Hello everyone, welcome to the day 12 of the machine learning teach by doing project. This will be the last lecture on the perceptron algorithm. Up till now we had two lectures on the perceptron. On day 10 we looked at the perceptron algorithm itself and why it works, and on day 11 we coded the perceptron algorithm from scratch in Python. Today, we will learn about some terminologies which are associated with the perceptron algorithm, such as linear separability of a dataset margin, etc. These terminologies are very important because when we look at ML models such as support vector machines and even some neural network loss functions such as the hinge loss, etc., many advanced concepts have or require you to understand linear separability and, more importantly, margin of a data set. And not many people know this, but perceptron is actually one of the first algorithms which introduced this concept in the first place. The concepts of margin and the concept of linear separability. So today we will be looking at four terminologies associated with the perceptron. The first is perceptron through the origin. Second is linear separability of a data set and what does it mean. Thirdly, we will look at margin of a data set and what is meant by margin of a data set. And finally, we will look at a theorem, which is an amazing theorem. We will not look at the proof of it, but it's called as the Perceptron Convergence Theorem. This will be a theoretical lecture where I will try to explain all the concepts in a nice manner. So let's get started. If you have not seen the previous two lectures on the introduction to the perceptron and secondly coding the perceptron algorithm, I highly recommend you to go through these lectures to clarify your conceptual understanding regarding the perceptron algorithm itself. So let's get started with today's lecture. I learnt about everything which I am going to show you today from MIT's course. MIT's course is one of the only course I found on the internet which actually goes into the theory of perceptron in a lot of detail. And the concepts which I am going to introduce to you today, such as linear separability, margin, etc. I have learnt all of them from this MIT course. I will provide the course material in the reference so that you can also go through it. Okay, so I have made all detailed notes for this particular lecture, which I'll be sharing in the information as I always do. So you will be having all this material which I'll be presenting in today's lecture. So let's get started. We already have seen about the perceptron algorithm, which is essentially a linear classifier, which means that let's say we have a negative data set like this and the positive data set like this. The perceptron finds the best linear classifier which separates these two sets of data. And then we looked at the algorithm itself. Essentially, the algorithm loops through the data about 10 times or how much ever we decide. And for each data point, we check whether a mistake has been made by the hypothesis. If a mistake has been made, the hypothesis is updated and then we cycle through the rest of the data set. We do this once for one iteration, and if we are going through 10 iterations, we do this entire process 10 times. One thing which will come up at multiple points in this lecture is this quantity yi multiplied by theta transpose xi plus theta naught. So recall from our previous lectures that the meaning of this quantity is that it illustrates whether a mistake has been made or not. So if this quantity is less than 0, it means that the hypothesis makes a mistake while classifying the point yi and xi. Whereas if this quantity is greater than 0, the hypothesis is correct. If it's equal to 0, it means that the point lies on the hypothesis. If you don't know why the meaning of this particular quantity means the number of mistakes or means if a mistake has been made, kindly look at lecture number 10 where we go through the basics of the perceptron. Okay, so this is the best line which is returned by the perceptron and is usually denoted by theta transpose x plus theta naught, where theta is a vector and theta naught is the scalar. The first concept which we are going to introduce today is called as perceptron through origin. It means that up till now we have been talking about theta and theta naught, right? And theta naught is kind of an offset. So if theta naught was not there, or if theta naught is set equal to 0, it means that y equal to theta transpose x. And that means that the line will just pass through the origin. And perceptron through origin is just a simplified version of the perceptron algorithm, where ultimately we find that classifier which best separates the data, but it also passes through the origin. That actually means just setting theta naught equal to 0 in the perceptron algorithm. So you take this algorithm and just put theta naught equal to 0 everywhere in this algorithm, and that will give you the algorithm for perceptron through origin. So you can see this is the algorithm for perceptron through origin. It's quite simple. Again, we check whether a mistake has been made or not. And this is yi into theta transpose xi. Theta naught won't be there since it's equal to 0. If the mistake has been made, we only update theta. Since theta naught is not there, as the line passes through origin, theta naught is always 0. So we don't need to update it. So perceptron through origin is just a simplified version of the perceptron algorithm. But many people use it to form theories about the perceptron, because if something works for perceptron through origin, it most likely works for the general perceptron as well, where theta naught is present. Perceptron through origin just makes it easier to prove some things about the perceptron, since we don't have to worry about theta naught. The second terminology which I want to talk about in today's lecture is called as linear separability. So a data set D is called as linearly separable if there exists some hypothesis, or if there exists some straight line such that yi times theta transpose xi greater than 0. Now remember what I said about this quantity yi multiplied by theta transpose xi. I said that if it's greater than 0, it means that the hypothesis makes no mistake. So basically, this definition says that a data set D is linearly separable if there exists a hypothesis which makes no mistakes on any of the data points. For example, consider the data set given by these crosses and the circles, and let's say and if someone asks you, is this data set linearly separable? You can even show them visually by drawing a straight line, and you can tell them that for this particular hypothesis, if you calculate this value, yi multiplied by theta transpose xi, if you calculate this value for all possible xi and yi present in this data set, it will always be greater than 0. And hence, and why will it be greater than 0? Because no mistakes have been made by this classifier. The positive points are on this side, which are all correct. The negative points are on this side, which are all correct. So no mistakes are made by this hypothesis, and hence the data set D is clearly linearly separable. Very simple definitions. The first two definitions are perceptron through origin, which just means finding a straight line which passes through origin. And the second definition is that of linear separability, which decides or which defines when is a data set linearly separable. And the answer is if there is a hypothesis which exists and which makes no mistakes on all the data points in the data set, that data set is considered to be linearly separable. Now we come to probably the most important definition in this particular lecture, and that is called as the margin of a data set. Before coming to margin of a data set, let me first describe or define what is meant by margin of a single point. So let's say this is the xy plane, and this is the straight line which is denoted by theta, and the normal lies in this direction which I have specified. And let's say we look at a point whose x coordinate is given by x and whose label is given by y. So first thing to note is that margin of a point always is defined on a labeled point. So if you just have the coordinates of this point without a label, the margin cannot be calculated. So you need two things to calculate the margin with respect to a point and a line. You need a line which is given by theta transpose x, since it passes through origin, and you need a point. You need the x and y coordinates of this point, and you need the label, whether it's +1 or -1. Now, the margin of this particular point with respect to this particular line is defined by this formula. y, which is the target label, which is the correct label of this point, multiplied by this terminology, which is called as, which is or mathematically defined as theta transpose x divided by magnitude of theta. So first I want you to focus on this particular quantity, which is theta transpose x divided by magnitude of theta. So in coordinate geometry, what this quantity means is just the distance or the signed distance of this point x from this particular line, which I have denoted by d right now. What I mean by signed distance is that, let's say this x is right, is on the positive side of the normal, right? So this quantity will be plus d. Let's say there is another point which is over here, which is exactly on the mirror image of x, but it is on the negative side of the normal. Although the absolute value of the distance of this other point will also be d, this quantity, the signed distance, will be equal to minus d, since this point is on the other side of the normal. So what this part of the margin definition represents, just the distance or the signed distance of the point from the line. That's it. And signed distance means that if the point is on the positive side of the normal, like this point is right now, the distance will be positive. If the point is on the negative side of the normal, then the distance will be negative. And we need to multiply this by the target label. So the target label, which means that what is the actual label with respect to this point. If it is plus 1, then the margin of this point will be plus 1 into plus d, which is equal to d. If this point is labeled as minus 1, or if its true value is minus 1, then the margin will be minus 1 into d, which is equal to minus d. Now, what I want to illustrate, or what I want to illustrate to you, is what does a margin actually represent. Of course, we know that it does represent the distance of a point from a line, but actually it represents a bit more. And through this representation, you will also try to understand why we care about this quantity. So consider 3 points, okay? Uh, so consider first of all this line whose normal is given in this direction, which is whose positive normal is given in this direction over here, which I am marking with the blue arrow right now. And consider 3 points x1, x2, and x3. Their true labels are all equal to plus 1. Okay. Now let us find the margin of all these 3 points. So the margin for x1 will be equal to the true label multiplied by the signed distance of x1. So the true label of x1 is plus 1, and the signed distance of x1 will be equal to positive d1. The reason it will be positive is because x1 lies on the positive side of the normal. So the signed distance is positive since this point is on the positive side of the normal. So the margin for x1 will be plus 1 into d1, which is equal to d1. The margin for x2 will be its true label multiplied by signed distance. So again, true label for x2 is equal to plus 1, and the signed distance is again positive because x2 is also on the positive side of the normal. So the margin for x2 will be plus 1 into plus d2, which is equal to d2. And if you look at point x3, the margin will be equal to its true label multiplied by the signed distance. So true label is plus 1, or the true y value, but the signed distance will be equal to negative because this point is on the opposite side of the normal. So the margin will be plus 1 multiplied by minus d3. So the margin of x3 will be equal to minus d3. So first of all, we see that for x1 and x2 the margin is positive, and for x3 the margin is negative. So margin of a point actually tells us two things. First thing it tells us is whether our classification is correct for that particular point or not. Now if you look at x1 and x2, since this is the positive side of the normal, our hypothesis will correctly classify x1 and x2 as plus 1, whereas our hypothesis will wrongly classify x3 as negative since it's on the other side of the normal, but its true value is point is plus 1. So our hypothesis makes a mistake on x3. So the margin actually illustrates whether our hypothesis makes a mistake or not. If the margin is positive, it means our hypothesis does not make a mistake on the point. If the margin of a point is negative with respect to the line or with respect to the hypothesis, it means our hypothesis has made a mistake on the point. Let me repeat that. If the margin of a point with respect to a hypothesis is positive, it means that the hypothesis has classified the point correctly, such as x1 and x2. Whereas if the margin of a point with respect to a hypothesis is negative, such as for x3, it means that the hypothesis has classified the point wrongly. So that is the first value which we can derive from knowing the margin. But the second most important value which we derive, margin also tells us that, okay, let us look at x1 and x2. Both are correctly classified, right? But x2 is better classified because it is far away from the our hypothesis. If something is closer to the hypothesis, it means that if the hypothesis was slightly on this side, x1 would have been wrongly classified, right? But x2 is so far away that it tells us that since the margin for x2 is higher, it tells us that we are more right on x2 than on x1. So apart from telling us whether we are right on the point or not, margin also tells us how right we are. So we are more right on x2 than on x1 because x2 is far away from the margin, which is good for us. Our margin can never make a mistake on x2 because it is so far away. Although our margin does not make a mistake on x1 also, x1 is closer, right? So if the margin were to somehow shift here, what I am showing with my arrow, it will classify x1 wrongly and it will still classify x2 correctly. So that is another insight which we derive from the margin. So margin actually tells us two things. It tells us whether we are right about our classification, that is one, which is indicated by whether it's positive or negative. But it also tells us how right we are. In this case, margin for x2 is greater than x1 because d2 is greater than d1, right? D2 is greater than D1. So the margin value tells us that we are more right about x2 than x1. So this is the meaning or the intuition behind the margin of a particular point. Now, now that we know how to calculate margin of a particular point with respect to a hypothesis, now let us define the margin of a data set. Let us define the margin of a data set with respect to theta. Uh, so margin of a data set D is basically the way you calculate it. You find all the points in the data set and you find all of those margins. You find the margin for each data point and then out of all those margins, you choose the lowest one. That's it. So the margin of a data set D with respect to a hypothesis theta is the minimum of all margins. So for example, consider this first example where this is the hypothesis which we have and we have 2 points here. This is the first positive point which is the and this is the second positive point. The margin of this point will be given by its sign distance which is positive. So let's say this is positive d2. The margin of this point will be given by positive d1. But the margin of this entire data set will be minimum of both those. So we'll need to find the margin which is minimum, which is d1. So then the margin will be equal to plus 1, which is the value of this point, into the sign distance, which is plus d1. So margin of this data set will be equal to d1. Now, by the way, this data set also has negative points here. But if you find their distance also, the sign distance will be negative, but the true label is also negative. So the margin is positive. But the distances of all these points from the line are much more than this particular point. So the margin will still remain equal to D1. Secondly, let us look at this particular data set. The first thing to recognize when you see this data set and this hypothesis is that these 2 points are classified correctly by the hypothesis and these two negative points are classified correctly because the normal is here. So the margin for this point, this point, this point and this point will be positive. But look at this particular data point. This point has been misclassified by the hypothesis because its true value is plus 1, but it lies on the other side of the normal. So the margin for this particular point will be negative. Now, when we look at the margin of this entire data set, we need to take the minimum of all margins, right? but the margin of these 4 points is positive and the margin of this point is negative. So the minimum margin will be given by this point. So the margin of this particular data set will be equal to minus d1. Why minus? Because the signed distance is negative of this point as it lies on the other side of the normal, and its true value is plus 1. So when you multiply the true value with the signed distance, you will get a negative answer. So I hope you understood the difference between these two examples. In the first example, first of all points were classified correctly. So the margin was positive. Then we had to look for the point which is closest to the hypothesis, which is this one. So the margin is equal to d1. Now if we look at this data set, this point is classified wrongly. So its margin will be negative. So if we look at all points, the minimum margin will be given by this point. So the margin of the data set will be given by the margin of this point, which is equal to minus d1. So before we come to the last terminology, which is the Perceptron Convergence Theorem, let us actually take a hands-on or practical example to demonstrate the concept of margin. So this example again has been taken from the MIT's course. Essentially, we consider three data points here: x1, x2, and x3. The true label for x1 and x2 is positive. The true label for x3 is negative. And this hypothesis theta is 1, 1, 1 minus 1, and theta naught is given by 1. The question is find the margin of this data set. If someone asks you this question, the way to solve it is start by finding margins of each point. So let me first find margin of x1, which will be equal to y1 multiplied by theta transpose x1 plus theta naught divided by the magnitude of theta. This is exactly the definition which we saw over here. It just theta naught was not there here, but we'll need to add that since it's present in the current example. So for this point x1, y1 is equal to positive plus 1. When we multiply theta transpose x1, so theta is equal to 1 and minus 1. So theta transpose will be this horizontal vector 1 minus 1, and the coordinates of x1 are 1 comma 3. So then the vector of x1 is represented by 1 3, and theta naught is equal to 1 as is mentioned at the start of this example. Also the denominator is equal to modulus of theta, which is equal to square root of theta 1 square plus theta 2 square, which is square root of 1 plus 1. So if you calculate this vector product and if you add this theta naught to it and multiply by y1, you will get that the margin of x1 is minus 1 by square root of 2. Similarly, if you calculate margin of x2, you will get that it is equal to 2 by square root of 2. And if you calculate the margin of x3, you will get that it is 2 by square root of 2. Now one trick which I want to tell you guys is that look at these, just look at it visually. So the normal to this data set is in this direction. So our hypothesis will classify everything here as positive and everything here as negative, which means that our hypothesis will make a mistake on x1. So just from looking at the data set, we know that the margin for x1 is going to be negative, whereas the margin for x2 and x3 is going to be positive. So just by looking at the data set, we know that the margin of the entire data set will be the minimum of all margins, right? So actually we will just need to calculate the margin of x1 since it's negative. We don't even need to calculate x2 and x3 since they are anyway positive. But now since we have done it, since we have calculated the margin of x1, margin of x2 and margin of x3, the last step is the margin of the data set. So margin of the data set is given by the minimum of all these three margins, which is minus 1 by square root of 2, 2 divided by square root of 2, and 2 divided by square root of 2. So again the margin is the one which is given by x1, which is minus 1 by square root of 2. So the margin of this data set is equal to minus 1 by square root of 2. This is how you have to calculate the margin of a data set, guys. I hope you have understood mathematically how to calculate the margin. Plus, you have also understood intuitively how we can calculate the margin quickly. If you have understood this concept about margin, it will really help us when we move to later ML algorithms such as support vector machines and when we understand concepts such as hinge laws, etc. The final thing which I want to show you all is a very cool theorem which is called as the Perceptron Convergence Theorem. So it turns out that there is actually a theorem which guarantees to us the number of mistakes which the perceptron will make. If you remember the coding assignment which we did, we looped through the code 8 to 9 times until the perceptron actually gave the correct answer, right? So people have actually found out a theorem as to the maximum number of mistakes a perceptron can make. And by mistakes, we mean this particular calculation. So as we are looping through the data, the perceptron makes many mistakes, right? And then we rotate it and correct the hypothesis. So this theorem states the maximum number of mistakes which the perceptron will make. So forget about this mathematics. I just want to tell you guys in words what does it mean, so that you understand it intuitively. We are not going to go through the proof in this lecture. If you want to go to through the proof, MIT has a lecture which is called as the proof sketch of the perceptron convergence theorem. So if anyone is interested, please go through this video lecture. It's an amazing lecture. Now I just want to convey the intuition to how this theorem, what this theorem states. Basically, this theorem states that you give me a linearly separable data set. Let's say the data set is linearly separable with a margin of gamma. Okay, so let's say the data set is something like this, where these three are my positive points and these five are my negative points. Okay, and the margin is gamma because this point is the closest, right, to the straight line. So the distance of this point is the smallest. So the margin of this data set is gamma. So if you have a linearly data set with a margin of gamma and where all the data points are within a circle of radius r, which means that let's say you start drawing circles from the origin and then you stop at a circle where you find that all the data points which you have are inside that circle. So let's say I start drawing circles of radius 1, radius 2. When I draw a circle of radius 2, I see that some point is still outside. Then I draw a circle of radius 3, which is shown here. I can see that for this circle, all the points are inside, right? So that is the value of capital R. So this perceptron convergence theorem states that if you have a linearly separable data set with a margin of gamma and where all the data points are located within a circle of radius r, then the maximum number of mistakes which the perceptron will make is r by gamma square. Which means that in this particular example, let's say that gamma, which is the margin of our data set, was equal to 1. And let's say the radius, which contains all the data points, is equal to 3. Then the theorem states that the perceptron will make a maximum of r by gamma square, which is equal to 3 by 1 whole square, which is equal to 9. Isn't that amazing? This is a mathematical guarantee that if we have such a data set, the perceptron will make a maximum of 9 mistakes. That's it. That's why the perceptron is so brilliant, because you can write mathematical proofs about it. What I now recommend you all is one thing. When we looked at the perceptron example in previous assignments, when we looked at coding the perceptron, we took a particular example, right, and we coded it out in VS Code. What I encourage you guys is to take a look at that data set again and do one thing: find the margin of that data set. And now I have shown you how to find the margin of a data set, such as this example. Find the margin of all points and take the minimum. So find the margin of the data set, call it gamma. Second thing you can do is find that circle which encompasses all the data points, and you can even do it visually. So maybe try a circle of radius 1 first, then 2, then 3, then 4. Maybe a circle of radius 4 will encapsulate all data. So find that radius. You can even do it manually on your graph paper. So find the radius r and find that margin gamma. And then mathematically, let's say if the radius is 4 and if gamma is 1, then mathematically the perceptron will make a maximum of 4 divided by 1 whole square, which is 16 mistakes. So mathematically the perceptron should make a maximum of 16 mistakes, and now you can check in your code how many mistakes the perceptron has made. So run your code, check the number of mistakes, and by mistakes you have to check every time the perceptron. So by mistake I mean every time theta transpose x plus theta naught is less than 0. This is a mistake. This is one mistake, right? So for every, as it iterates through multiple points, try to find the mistakes it's making, and then try to check whether the theoretical value which you computed makes sense. This is why I really like the perceptron, because for many ML algorithms it is very difficult to find theories like this, that this algorithm will only make these many mistakes. But for perceptron we can write mathematical statements such as these. I deliberately wanted to show you guys this so that you have a foundational understanding of why the perceptron works, and also the fact that there is a guarantee that the perceptron will work if we have a linearly separable data set with a margin gamma and where all data points are within a circle of radius r. These are the properties and the power of the perceptron algorithm. Okay, so that actually brings us to the end of this lecture. In this lecture, we looked at four concepts. We first looked at perceptron through the origin. Then we looked at linear separability of a data set, which just means that if there is a hypothesis which does not make any mistake on the data set is linearly separable. Thirdly, we looked at a margin of a data set, and we saw that. So first we looked at a margin of a point, and we saw that the margin not only indicates whether our hypothesis is correct or not, but it also indicates how correct are we. So if a margin is positive, it indicates that our hypothesis is correct for that point. But if a margin is more and more positive, it means that our point is far away from the hypothesis, which means that we are more right about such points whose margin is very highly positive. Then after calculating the margin of a point, we also saw how to calculate the margin of a data set. Essentially, when we calculate the margin of a data set, we just have to take the minimum of all margins. And finally, we looked at the Perceptron Convergence Theorem, which states that if we have a linearly separable data set with a margin gamma, and where all data points are within a circle of radius r, the perceptron will make a maximum of r by gamma square mistakes. I also gave all of you an assignment towards the end, where you can look at the code which we saw in the last lecture. I have also provided the code. Look at the points in that code. Find the margin for all those points, which is gamma. Find the circle within which all those points lie, whose radius will be r. Find r by gamma squares, r by gamma whole square, and then compare it to actually how many mistakes the perceptron has made while you are executing your code. This is an amazing assignment. So to those who complete this assignment, I will specially highlight your name and your submission in the next lecture. So please try to complete this assignment and submit the solutions as YouTube comments, and I will specially discuss that solution before the next lecture starts. Thank you so much everyone. Thanks for sticking with me up till lecture number 12. We have received some really positive feedback on all the lectures which we have been preparing. And there are so many more things to be done. We have linear, so after this we have support vector machines, we have logistic regression, then we have I think then we talk about linear regression, then we will go through practical examples of regression in Python, then we will go through neural networks, then we will also go through recommendation system towards the end. So there are a wide range of things which we have planned for you. So thank you everyone, and please write down notes and execute the codes which I have been showing you. That will make sure that the learning is maximized. So thank you everyone. I'll see you in the next lecture.